Hello everyone, and welcome back to another lecture video for the course of database design and implementation. In the last week, we discussed about the course syllabus and introduction to the different topics that we will be covering in this course. So to recap last week, the contents that we had discussed was the syllabus, and thereafter we talked about the importance of the course, as well as what are the different topics that we will be covering and why these topics were important. Okay, and along these lines, if you recall, the few things that we discussed is in terms of design and implementation, of databases, there were a few key things that we need to address, right? And with respect to design, we had talked about what is known as the conceptual design of databases. Okay, and with respect to implementation, we had discussed about what is known as the logical design of databases, as well as the physical design, where the physical design is basically out of scope, right? So what we are going to cover is mostly about the conceptual design and the logical design. And in addition to these two main topics, there were some other relevant topics that we had discussed, which was along the lines of transaction management, query optimization, and performance tuning of our databases. So this is what we had discussed in the last week with respect to what we are going to be covering in the duration of this semester. So in today's lecture, our agenda is first of all going to be covering some basic definition that we need to be familiar with before we start discussing about the importance of databases and its design. Okay, so I'm going to introduce some terms that we need to be familiarized with in order to be able to relate to some of the motivations of why we need to focus on the design of the database before we can move on to its implementation. Okay, and most of these definitions are going to be introduced in an informal fashion. Okay, thereafter, we are going to talk about the importance of database design. Okay, so why just by using a database doesn't solve some of the prevalent problems that we have with respect to storing data and then processing it, right? So we are going to discuss that within the topic of why database design is so important and why does it form the foundation of this particular course. Thereafter, we're going to learn about the evolution of data storage and processing. Specifically in this topic, what we are going to learn is about file systems. Okay, how they used to store the data and what were some of the challenges or shortcomings that was faced by these file systems. So once we understand those shortcomings, we will introduce ourselves to database systems. And database system is basically composed of databases plus database management systems. So we are going to learn what are the different components of a database system and what are the benefits and the functionality of the DBMS that helps us to address the challenges and the shortcomings that were present in the file systems with respect to data storage and processing. But in learning all of this and in discussing all of this, we have to keep in mind that a database system is only as good as the design of the database that you help to produce, which is the conceptual design part that we discussed last week. So it is very important that we discuss this first before we move into the different storage units or the storage structures or the computer structures that helps us to store data and understand those structures. Okay. So moving on and looking at some basic terms. And their definitions. So the first and foremost term that we have, or the first and foremost thing that we need to know, is basically what is the difference between data, information, and knowledge. Okay, so all of this course is not of any worth if you don't understand the distinction between these three things and what meaning they're trying to convey. So think about an example where you have a file, you have downloaded a file from the internet that consists of informations or which consists of records such as 25, 26, 30, 32, 33, and let's say 17. Okay, so how many do we have? 6. And let's put one more here. And you have some similar information here. So it's kind of like a two-dimensional array, and you can call it A of ij, right? And then you have the rows as 7, and then the columns could be any number of values. Let's call it n, right? And n is equivalent to, let's say, 48, something along these lines, something natural. Okay. So if you download a file from the internet like this, and if you see numerical values such as this, the first question that you need to ask yourself, that even if you store this, do they convey any meaning, right? So the question that you're asking yourself is there any meaning behind these numerical values that you are seeing on the file? or whatever document type that you have downloaded from the internet, right? Similarly, another example could be from the domain of, let's say, machine learning, right? The object or the objective of machine learning algorithms is primarily for classification of images. So if you go to any image repository, okay, and then you download a bunch of images, let's say image 1, image 2, and so on, right? If you just simply download them and store them somewhere, do they convey any meaning, right? And so on and so forth. You can have many other different examples along these lines. So the format of these files and what they consist of, that is these numerical values or any different types of data that you can have, it could also be characters, right? If they don't convey any meaning, if they only have what is known as raw facts and figures, then that is what we call as data. Okay, so if we want to define what a data is, we can say that it is simply raw facts and figures which has not been processed to reveal any meaning. Okay, so that is what data is. But if we come to the domain of information, then if you have already guessed, then processed data generates information. Okay, so that means if we add context or background meaning to data, and then we process it by applying some sort of procedure, given the nature of information that we're trying to extract, then through that processing, we are able to generate information. So that means in the context of our running examples, if we said that these values that we are storing are temperature values, right? So we are adding some context or some shape and form to the data that we collected, right? And then we can say that if this is temperature values, then the recorded temperature values are in Celsius. Okay. Then we can also give some more context and say that the rows or the columns that we have are basically days of the week, and that the rows that we are going to have are basically the week number, or something along these lines, right? So this will give some more context to the data, and it will increase our understanding of what the data is trying to convey. Because remember, initially when we were looking at this example, we asked ourselves that if we simply look at these numerical values without any other related information, then do they convey any meaning? And the answer to that was no, a resounding no, right? But now that once you have added some of these very basic information, that oh, this is what the numerical values is trying to convey, right? This is the unit of their measurement, right? And then the columns are conveying this information or this meaning, and the rows are conveying this meaning. Intuitively, we can relate to the fact that, okay, this is what is happening in this data collection or in this kind of file. All right. So similarly, if we get the images And we can add some context that these images are mostly related to the task of, let's say, classifying whether the image is a cat or not, right? So then when we get that, we kind of have an idea of where we need to go with this, or what we can do with it, what kind of processing that we can do with it, right? So there are generally two things when you're trying to generate information, two steps that you need to address. The first step that you will need to address is basically what is known as pre-processing. And this is because the process or the procedure that you're going to apply to the data in order to transform it to information will require all the records or all the numerical values or alphabetical values or the images to be in a certain format that is coherent to the nature of the procedure that you will apply, right? So for example, if you're trying to, in this particular example of our temperature data, you're trying to guess, or not guess, but compute or evaluate or predict the forecast for the upcoming few weeks, right? You're trying to apply some sort of statistics and probability likelihoods by processing the data and then trying to figure out what it is going to be like in the next week or so from the end of wherever your record has stopped, right? That is what you want to do. So now it is quite possible that whenever the weather service agency was collecting the data, there might be some missing records, right? So you have to remove those missing records such that it does not skew the result of your procedure that you're going to write for the forecasting process, right? Similarly, there might be some misreported information while somebody was recording the data information. So instead of, let's say, recording 30, they forgot about the 0. So it's just showing us 3. So suddenly, from a human perspective, we can see that, oh, everything was close by. It was 18, 25, 26, but then suddenly 3 and then 32, 33 and 17. It seems a bit abnormal, right? So that is what the task or the job of pre-processing is. It needs to clean the file and make it ready in such a way that the procedure that you're going to write and apply to transform the data to the information is compatible with it. And of course, the second step is to add context to the data. So without this context, as we discussed, a lot of the values that is stored in your database or in your file systems will not have any meaning, right? So it is quite essential to add context to the data. So sometimes all this context results in a particular another separate file to any kind of data that you have collected, which will be known as metadata. Okay. So what is metadata? Metadata is basically data that describes the original data file. Okay. So we will discuss metadata a bit later on when we move towards the design of databases. But for now, you just need to know that data that describes the structure and content of actual data. Okay, so that is what metadata is. So now once you have processed once you have collected your data and you have processed them, pre-processed them, and then added context in order to generate information, what remains thereafter is basically knowledge. Okay, so knowledge is nothing but the familiarity, understanding, and awareness of information. So once you are familiar with the information that is specific to the problem domain of your field, once you have an understanding or an awareness of it, then what you have related to the stored data is known as knowledge about that particular field. Okay, so whenever we are mentioning data, we mean or we refer to just regular raw facts and figures that does not have any kind of meaning. Right? So they're just numerical values or alphabetical values or images, video feeds. It could be any data type. Okay, and if you process them and add some context to it, then what you generate from the data is known as information. And once you have familiarity with that information, then what you have is basically known as the knowledge about the problem domain that you are dealing with. Okay. So after that, a few things that you need to know. So we talked about data. So the next three things that we are going to be discussing are the terms that you should be familiar with. So I'm going to write them all. Let's keep them separate. So the first thing that you need to know is what is a field. Okay. So in terms of data storage, when you're storing a data, what is a field? Or sometimes it will be called as attribute, or sometimes it will be just simply referred to as columns, database columns. Okay, so field is a terminology that is used in file systems, and then attributes and columns are terminologies that are used within the database system domain, but essentially they mean the same thing, and that is a character or a group of character which could be both alphabetical or numeric or a mixture of it, that defines the data. Okay. Thereafter, you need to be familiar with the term which is known as a record. What is a record? Okay. So record is basically a collection of fields that is used to define a person, place, or a thing. Okay. So record is a file system terminology, and within the database terminology, it could be referred to as a row or an entity instance. Okay. Sometimes interchangeably, as we move forward with this course, the entity instance will be simply referred to as entity. But in actual strong definition or in actual terms, entity is not the same as an entity instance. But later on, it is kind of one of those computing areas where which you might have encountered in different subjects as well, is that the terminology kind of becomes gray and starts to be used interchangeably, right? So don't get confused. It kind of means the same thing, but we want to keep them differentiated for now, okay, until we don't have to deal with the difference of the meaning that it actually conveys. So for now, just think of it as entity instance and not entity itself. Okay, and then finally we have what is known as a file. So a file is basically a collection of logically related records. Okay, so file is, of course, as you have already guessed, is the term that you use within the file system domain. But within the database domain, we sometimes call it a table, of course, in the relational database domain, or we call it an entity. And this is where the difference between entity instance and entity is, right? Because entity instance is an instance of the overall entity, all right? So these are some of the terms with respect to the design. When we will be talking about the design of the storage of our data, whether it be within the file system domain or whether it be within the database domain, these are some of the terminologies that you will very frequently encounter. So in addition to these three that we discussed right now, what you also need to know is the basic difference between data and information. So again, with respect to the idea that we talked about here, that sometimes entity gets interchangeably used in the place of entity instance, later on you will also see that the difference, the distinction between the actual meaning of data and information gets muddied as well, and it starts to get, or it starts to being used a bit interchangeably as well. So again, keep in mind as a note that for now we will stick to the distinction that these terms provide. That is, we will call data as raw facts and figures, and information being processed data after we have added some context to it. And similarly, entity instance is a particular row within the entity or the table, okay? And they're not the same. All right. So other than that, we will come to some of the other terms as we move forward with this lecture, with today's lecture. But before that, the first thing that we need to ask yourself is, why do we need a storage structure like a database? That is, what is the importance of database? Why do you need a database in particular and not any other storage units, right? So the reason behind that is two things. The first one is the technological trends. Of, let's say, the past 30 years, right? And what I mean by this is that data is becoming more and more ubiquitous and pervasive. So an example, so that data is present everywhere and it is also encroaching the way of our life. And a good example of this will be all your smart devices that you have in this day and age that you use to interact with different businesses, right? So when you say smart devices, it could be in the form of a smartphone, it could be in the form of a smartwatch, you can have your tablets, handheld devices, and I don't even know what else is available there in the market, but you get the idea, right? And we use all of these devices, which makes the data collection pervasive, right? It relates to our way of life. And since we have access to these devices and the growth of internet and cell connectivity has improved over the last 30 of the years, then the data that is generated by these devices makes the availability of data everywhere. You don't have to go to specific terminals or specific portals in order to be able to access a device which is capable of communicating over the internet or over a network, okay, a personal network. So those changes has made data quite prevalent. right? And you use these devices as users, as customers. We use these devices to interact with different businesses, right? So from a business perspective, we need to know that who all are our customers and how should we run our business in order to deal with these customers, right? So that means that when we are interacting with our businesses, data is the foundation for running a good business. I don't know if you have heard this term before, but in a few more years, 10 to 20 years, and even at this point of time, data is more costlier than oil, right? So data, the currency of data is going to become more and more important as we move forward, right? So for both of these things, that is the prevalence of data, and that data is the very foundation for running a good business, because that helps you figure out, identify your customers, right? The needs of your customer, and we can also say who are your employees. And then we can talk about who do you owe money, and who owes you. So all of these decision making comes from the data, and that data is quite prevalent, and it's being generated at a very fast speed, right? If you have heard the concept of big data. So to address these two different facets, right, we need a storage structure that is able to accommodate the speed at which the data is being generated, and then present the data in a structured format such that businesses or even customers can kind of process that data and get the information that they want in an ad hoc fashion. So that is the most important thing. The word from there, when you're trying to extract some information from the stored data, the nature of that extraction is ad hoc, which also means on demand, right? So it couldn't be like you have a storage structure, and it is trying to store the information about your business, and then you want to know something. For that, you have to, in a sort of way, in a manner of speaking, you have to raise a ticket, right? And that ticket will be processed within 48 hours, and then you will get the result back, right? That is something that nobody would like, right? If you're a customer and if you're interacting with, let's say, Google Maps, and you ask Google Maps that what are the nearest coffee shops that are open right now. Right now could be any time, whenever you are raising that query, right? And Google Maps gives you the result that your request is being processed. We will get back to you within 48 hours. No, that is not going to work, right? So we need an efficient storage structure which is able to handle this large volume of data that is being generated, and store it in such a structured way that it is able to deal with any of these ad hoc / on-demand queries that will be executed against it in order to produce the result as fast as possible. And that is why we need database systems, right? In addition to that, it also solves some of the challenges that older generation of storage units had faced, right? Specifically the computerized file systems. So we will talk about that in a few minutes right now, right? So this is the importance. So, but the question is now that if you just introduce database, will that solve everything? That is, will that solve the need to be able to store the volume of data that is being generated here? Will that be able to write intelligent queries by itself and then be able to generate the required information as per the need of the customers or the people who are using the databases, that is the organizations? Well, the answer to that is no. And that brings us to the next topic, which is basically the importance of a well-designed, well, importance of a well-designed database. Okay. So the reason why we are discussing this topic is simply using a database does not solve the challenges that may be present with respect to storing the data and with respect to writing queries that will be able to efficiently generate the required result whenever it is being demanded, right? So you can relate to that with respect to programming. If the algorithm of the program that you are going to design is not good, okay, then regardless of how good of an implementation language that you use, you might be using the best language, most up-to-date, fastest compiling language that is available to you, right? But if your algorithm is not well designed, then you are not going to get good results, right? It's going to struggle, right? So the same idea applies in the domain of databases as well, because we discussed in the very first lecture is that there is a correlation between the database lifecycle and the software development lifecycle as well. So design is very important. All right. So let's take a look at an example to understand the importance of a well-designed database, right? So why a well-designed database is necessary. So let's take the problem domain of, let's say, universities. Okay, and in that we are talking about a subdomain of student records. So what we are trying to store is the courses or student personal information and courses they registered or they enrolled. They are enrolled in. Okay. So this is what we want to, let's say, store. So what is the intuitive design strategy that we are going to follow in order to store this information? So first and foremost is the task of identifying. So remember, if you are trying to create a table or a file, just a quick recap of what we had talked about a few slides back. This is a table in the realm of databases, and within the realm of file systems, it is just known as a file. So file is a collection of rows, right? So these rows are known as records, or they are known as just simply rows. And what was rows? Rows is basically a collection of different fields which defines a person, place, or a thing. So here, what is the person, place, or a thing? So we have a person here that is the student, right? So that is what we're trying to store. So each of the records and a row is basically going to reflect a particular student. So it could be student 1, student 2, and so on, right? And then within that file, the columns that you have are basically going to describe the data related to those particular place, things, or objects that we are trying to store in that particular file, right? So these columns or these attributes are going to describe the data that is used to describe the object that we are storing in the file, right? So that means the question that we are asking ourselves is basically, what are the attributes which defines the student that we are trying to store, right? So the goal of our storage is basically the personal information along with the courses that they are enrolled in, right? So what kind of fields or what kind of attributes will you use in order to define a particular student that is going to express or that is going to store the information about their personal records and then the courses? So we can think of attributes such as an ID, right? And then we can talk about, let's say if it is the Oakland University, then we will have the Grizzly ID. So this ID here is basically the row number that we have in the storage location. Whereas the Grizzly ID is something that is more practical, that has been assigned by the university. It does not necessarily exist in the real world, but it has been assigned for improving the processing capacity or the processing capabilities of your database, right? So thereafter, of course, you will have something more basic, such as student name. Okay. So then what else will you have? You can have something like student date of birth, right? Then you can have student join date. So the date when they joined the university, right? Which fall semester of some year, right? Something along those lines. So these are some of the examples of some of the personal identifying information related to a student. Okay. So that is, you can add many more. You can add address, phone number, etc., so on and so forth. But let's keep it like this. And then the other set of information that we want to store is basically the courses that they are registered in. So we can simply say course ID, course number. Let us just restrict it and call it course name. Okay. So now that we have identified what is going to be a row or a record in our storage for a given table, and then what are going to be some of the typical columns, let us just put the design in place, right? So that means we will have a table or a file which is, let's say, student ID, and then student Grizzly ID, then student name, then student date of birth, then student, let's just not go for the last one, reduce it a bit just for the sake of simplicity, and let us just say course name. So this is our intuitive strategy. So we put everything in, and then you can have some student ID, and let's say that is 001, and then Grizzly ID would be G something something, right? And student name could be, let's say, John Doe. Student date of birth could be 0101 2000 2000. And then course name could be database. Okay, so let's call it database systems. And then you can have another student. Let's give them some dummy values as well. So it could be G5567. Let's give it some value as well, 9962. And this could be Jane Doe. And then she could be 5695, something along these lines. And then let's say the course name is System Administration, sysadmin. So these are some of the initial design structure that we can intuitively come up with given this particular problem that we are trying to design. Right? So now let's look at a few things that can come up. So if, of course, a given student, we all relate to this fact, is that they don't register to this course, one course in a particular semester, right? They have multiple courses. So now in this particular structure, if John or Jane is enrolled in more than one courses, which they will probably be in majority of the cases, then how are you going to write that? So there will be two options that is available to you. The first one is you can repeat the whole thing and then you can add the different course that they're enrolled in. So what I mean by that, so if Jane wants to enroll in, let's say, a course called, let's say, is Intro to Programming, let's say C++ programming, something along these lines, right? So they want to enroll in this particular course. So one option that is available to you is you can repeat all the personal identifying information for Jane and then add a C++ for the course name. But this is problematic now because you have, as far from the physical format of the data is concerned, as far as the design is concerned, now you have two rows or two records with similar identifying information. Later on, when we talk about what is known as the primary key of tables, we will see that it is mandatory. There is a rule which we have to follow with respect to design that does not allow us to have the primary key to be identical for any two rows. So this technique is essentially not favorable, right? So we have to avoid this. So what is the other option? So the other option, to prevent any kind of duplication of the student ID problem, we can have another column and we can call it course name 2, right? And here we can add C++. So now what are the issues of this particular design strategy? So the first problem is anytime a student enrolls for a new course that is more than the number of attributes that is already present, then you have to redefine your design and you have to add a new column to it. Okay, so that means if Jane was registered in, let's say, 3 courses this particular semester, so system administration, C++, and let's say DB, databases. And then John was registered in computer programming, and then there was no other course for John. So this will be course name 3. So John was not registered in any other courses. So now that this whole design has been established, what are some of the glaring problems that we have at this point of time? So you should pause the video right now here, and then you should ask yourself that, okay, we avoided the problem of the duplication of the unique attribute within the tables. right, which is the student ID. We avoided that. And so the solution, the alternative solution to adding more courses associated to a particular student record was to add more attributes for different course names. And this is what it looks like currently on the slide, right? So what are the issues is the question. So the issues are basically, first and foremost, that if any student registered for less than the maximum amount of courses that a particular student has registered. So that means in this particular case, Jane has registered for 3 courses, which is the maximum. So that maximum value is kind of dictating how many attributes or how many columns you need to add in this particular table, right? So if any student who has not registered for that maximum number of courses, who is not enrolled in that maximum number of courses, they will have what is known as a null value for that particular field, right? And having null values within your database design is not a good thing because it kind of impedes the operation of different arithmetic operations that you need to perform when you are writing queries for your databases, right? The other problems that you can have is you will have to change the structure of your entire file or your entire table anytime a student registers for a set number of courses that is more than the current maximum. So that means if you have, let's say, another student, whatever be the GID, and then it could be, let's say, the rock. All right, even he has to study at some point. So they had some database, and now if the rock registers for, let's say, 4 courses, then you have to add another column at the end, and that will create more null or dummy values for the existing students. But the key point here is you have to manipulate the entire file structure or the entire structure of your table, and that is again not desirable. Okay. And the other issues that you can have here is if you have noted here the way I have written it. If you were responsible for entering the record for John and somebody else was responsible, there was a different system administrator or a database administrator who was responsible for plugging in the value for Jane, or they themselves are responsible for providing those values, then there is a good chance that John may write his course as database systems, and then Jane may write it as databases. However, as far as the process of storing the data is concerned, these 2 courses are essentially the same, right? But however, from a physical storage point of view, the computer will treat them as different and will not be able to tell that they are actually the same because you have encoded them differently, right? Also, the same problem is here, C++ and then computer programming. Maybe these 2 courses are the same, but the computer won't be able to tell the difference because you have encoded them differently. So there is no standardization with respect to how the data is being recorded. Okay. Other than that, some minor problems that can come up is if you want to, let's say, alphabetically sort this particular column, right, on the last name, then there is no way of doing this other than writing separate procedures, separate procedural programs that will read the data from these columns and then return the results, and then you have to apply them from the records. So that means given the nature of the data that is being stored in these designs, you have to write separate procedures that will be able to deal with them. And you cannot inherently use some of the primitive techniques that are available for database queries in order to process this data. And that is just because the way you have designed it and nothing else, right? So what I mean by a separate procedure when you're trying to alphabetically sort based on, let's say, the student's last name, is you can read this data, You can write a string manipulation program, then you can alphabetically sort, then you can use that result of the alphabetical sort as a reference in order to extract the rows one by one from this table, which kind of makes the use of a database moot, right? There is no purpose of using a database anymore if you are going to write your own procedures in order to manage the data and in order to deal with it, right? So that is one of the problems that you will face here in this particular design, our intuitive design strategy. There could be other problems is, let's say if a professor introduces a course, right? And let's say that course name is some special topic. So there is a special topic course on let's say security, right? So from the university's perspective, we want to keep this course on record, but none of the students have registered for it, right? However, the only place where you are listing course name is this particular design right now from this design strategy, right? So if you do that, then instead of creating dummy records for course name, now you have to create dummy records for student, because there is no student who is registered for that particular course, right? And that will also again create a challenge. So the design is very important. That is what the goal is from discussing all of these issues, right? You cannot simply just figure out what your problem domain is or what your subdomain within that problem is. And you cannot just simply put all the data in together. So an insight, so into good DB design. And the reason why I write insight is because the majority of the course or the majority of the topics that we are going to be covering in this course is to help us learn the approaches, the well-defined approaches, the well-defined techniques, the heuristics that has been established over the last 3 decades in order for us to be able to generate good design. And design is the focus of this particular course, right? So that is why I'm saying insight, is because I'm giving you a brief glimpse into how you can improve the design. And later on, as we progress and we move on to chapter 3, 4, 5, and 6, we will look at actually what the well-defined techniques are that will help us every time produce a good design for our database, right? So the insight is you have to basically separate the data that you're trying to store based on context into different files or let's call it tables within the database domain, and then link them. So how we are going to link them? That is something which will be guided by the type of data model that we are going to be using, because the data models is going to provide us with the key ways in which we can link them. The separation of the context is also something that we can do by simply applying the algorithms or the techniques of normalization. And that is why, again, going back to revisiting the fact that this is the reason why we are learning all these topics. Okay? So, as a self-exercise, for this particular example that we discussed here in this particular slide, try to apply this technique of separating the data based on the context and storing them into different tables by yourself, and then finding a way to link them. And a hint in that aspect is when you're trying to link them, is you are creating another linking table. So that is the hint that I will provide you with, right? So of course you can guess to a certain degree that the two contexts that we had in the example that we discussed are basically the student's personal information and the courses that they're enrolling in. So that will result in two tables. But when you're trying to link them, you will also have to generate another table which will be responsible for linking them. So as a self-exercise, try to improve the design or try to improve the intuitive design of the previous slide by separating the data based on context and then linking them. Okay. Essentially, the goal that we have here by trying to do this is to avoid some of the problems that we have discussed in this particular slide. That is, we should not be required to change the entire structure of our table every time that we are trying to add a new information. We should avoid duplication of the primary keys or the keys or the columns that should remain unique. We should avoid its duplication. We should avoid the creation of null values as much as possible. Of course, at times you won't be able to avoid it, but if it is quite straightforward and you should not have it, then you should avoid that, right? And similarly, we should not create any kind of dummy records. Okay, so please try this by yourself and see how it goes. All right. So after that, the next topic is basically the evolution of data storage and processing. Okay. So initially, most of the data storage was manually, right? When you say manual, you can think of logs, diaries, journals, and so on and so forth. So most of these ways of storing and processing data was reliant on basically pen, pencil, and paper. Okay. But what happens as globalization increased, right, and the demand for a particular business or a particular organization spread across different regions, or the number of customers also increased for that particular organization or for those kind of businesses, it became increasingly challenging for us humans to be able to manage the growing volume of data just by using pen, pencil, and paper. Because initially, if you had opened a coffee shop uh, in let's say a particular neighborhood, right, and in your locality, and you had like 30 customers, then it is fine. You can just maintain all the logs: who bought what coffee, which date, how much do they owe, if they do owe anything, who are your customers, where they live, so on and so forth, right? How much coffee you have to order for them given those customers. nothing was that busy, nothing was that rushed, so everything was manageable, right? But now if you kind of grow from there, your business, and come out of your locality and neighborhood, and you start to become a chain, and you spread across different regions, different neighborhoods, and your customers from 30 becomes 3,000, and then the next day it becomes 30,000, and so on and so forth, right? Assuming that it's very good coffee, right? So as that happened, it was quite difficult to keep up with pen, pencil, and paper, right? But at the same time, when that was happening, and this was around the 1960s and stuff like that, when that was happening, the computing technologies also started to evolve as well, right? So that evolution took us to what is known as the computerized file systems. Okay, and thereafter there were some challenges and shortcomings which was present in computerized file systems, which is basically the issues of data redundancies and anomalies which needed to be addressed, right? So in order to address these shortcomings, resulted in the adoption of creation and thereafter the adoption of database systems that we are following till today. Okay, so here specifically we are going to be talking about the computerized file system. So the computerized file systems looks similar to the intuitive database design that we discussed in this particular slide. Okay, the difference from manual file systems was that it was stored in a particular computer. And specifically what we are going to talk about is the problem that they had with respect to their management and their implementation. So let's look at some of the shortcomings that we had in the computerized file systems. So I'm just simply going to write file systems. Okay. So again, remember, I'm not going to delve into the structure of the computerized file systems because they are similar to the intuitive database design that we discussed a few moments back, right? So I'm just simply going to talk about some of the challenges that were present in the computerized file system domains, which were required to be addressed and thus led to the evolution from the computerized file systems to the database file systems. So the first issue, or some of the first challenges that we had, is that there were lengthy development times. And the reason behind this is because the computerized file systems were developed based on the needs. So as the needs arise, the structure of the file system was changed in order to meet those needs, right? So there wasn't any chance of kind of like on-demand operation, and you could not respond back to the requirements as soon as possible. It took at least a few days in order to do that, right? So this led to the problem of not being able to get on-demand service, right? So that is no quick response. So after that, the management of these file systems was tedious. Okay, so that means that you had to write your own procedure which is specific to the structure of the file system that you have developed. And if anything changes with respect to the structure of the file system, then you would have to change all your management procedures in order to match the change that you have introduced, right? The last part was that it had different ownership of the same file, of the same set of files. So what this resulted in, or if you want to have an idea or a glimpse into this particular problem, think of that you have an organization, right? In the organization, you will have different departments, right? So there could be a department with respect to HR, human resources. There could be a department with respect to customer relations, right? And there could be a department with respect to finances. And there could be an R&D department, right? So now, if you are developing file systems, all of these file systems or all of these different departments had their own set of files, which was tailor-made to satisfy the objectives of these particular departments, because the goals of HR is not going to be the same as that of R&D. But there was a chance where the R&D might have a set of files which the HR also need to maintain, right? So that means the R&D might maintain the files of, let's say, employees, right? But the HR will also need a file system of employees, right? Similarly, here, customer relation could have some information about customer, let's say, balances, right? That is, what is the amount of money that you owe to the customer or the customer owes you, given the nature of your organization, right? So similarly, that could be present in finances as well. That is, what is the customer balances. They're having the same file, but the objective of processing that is performed on these files are essentially different, right? And that is the reason why they are writing their own procedures in order to maintain and manage these kind of files. So the issue now is that there was no synchronization between these different departments, or even if there was, it was not, instant. So this final issue led to the problem of data redundancy and data anomaly, right? It also created an issue with respect to lack of security of data, as well as limited data sharing. Okay, so all these issues needed to be addressed, but the major problems was along the lines of data redundancy and data anomaly. So let us look at what these two issues are, and why they are not desired in the database design. But if you read between the lines, we have already discussed about it in the poorly designed database example that we were talking about a few moments back. But again, we will revisit some of the concepts that we have talked about it, and formalize the notion of data redundancy and data anomaly. Okay, so let's look at data redundancy first. Redundancy. Okay, so what data redundancy is essentially is basically the same copies of the data appearing in different locations. and this can lead to a lot of problem, which is in the form of data anomalies and and other kind of issues that is caused due to data anomalies, right? So in order to understand them both side by side, we have to talk about them at the same time, right? Because one leads to the other, is what I'm trying to say, right? So we are also going to talk about or take a look into data anomalies at the same time while we are talking about data redundancy. So data anomalies are of three types. The first one is insertion anomaly. And then you have deletion anomaly. And then you have updation or update anomaly. Okay. So what it means here is if you have multiple copies of the same data, that might create a scenario which leads to data anomaly. And if you have data anomaly, then you will have incoherent data storage within your file systems. Okay. So to look at the first example of insertion anomaly, what it means is that if you create dummy data within your files or within your tables, then that is known as insertion anomaly. So an example of insertion anomaly, if we look at our previous example here, is when we were trying to, let's say, enter this special topic course, when we were trying to insert this data value, but there was no students who were enrolled in it. Given the nature of this design, we had to create some dummy student values. So it could be null or it could be student values which has no meaning, right? So this is an instance of an insertion anomaly. Okay. Then you have the case of deletion anomaly. So let's say if you delete a particular, so let's say somebody had registered for this particular special topic course, right? So somebody along the lines of, let's take a different example. Yeah. So let's say there was 004 and then some GID and then some name, let's say Harry Potter, right? Some date of birth, and Harry Potter had registered for the special topics course. All good, okay? And then you have null values or dummy entries after that, all right? So then, if let's say after a semester, the special topic course was not offered anymore and it needed to be deleted from the file system. So then what will happen is you will remove this whole row, because when you delete, you don't just delete based on one particular course, you might end up deleting the whole row itself. And then you have deleted essentially a student record who is still an active student with the university, right? So that is an instance of deletion anomaly, right? And then update anomaly can happen from, let's say, trying to update the name of this course DB systems, right? So for example, from databases, let's say it becomes file system management, something along these lines, right? So you need to update the name of the course, or you want to create a new advanced course, but you want to name them as like database systems 1 for the undergraduate level and then database systems 2 for the graduate level, right? So you want to separate the two courses and then offer them separately, so you want to rename the courses. So you are able to rename it here. So you give the one for that particular student, but later on, because it exists for different students as well, like here, then you forget to give the new updated name. So you're not updating it across all the redundant copies of the same data that exists, right? And this can not just happen within a single file. So this was a single file environment, right? So this, all the issues or all the anomalies that existed was present within a particular file itself, right? But essentially, when you have different ownership entities, like for example, in this case, where you can have the same set of files being managed by different departments. So that means the same set of information or data exists across different files as well. So even in those instances, you can have the issues of update anomaly, because what can happen is, let's say one employee may leave the R&D, right? So that information the HR knows. So they remove that employee information from the file employee, which is managed by the HR, but the R&D department did not know that yet, right? So there might be a period of time where there might be a mismatch of data. So then the R&D department might be telling the finance department to pay that particular employee, but the HR has removed the record. So if, unless and until the HR makes an active effort in order to make sure that in all the files where this employee record was present, it needs to be revoked such that no operation is performed with respect to that employee, then it is going to be a problem, right? So we have to keep that in mind, that due to these different ownership entities, these issues due to different ownership entities leads to data redundancy. And if there is data redundancy, then we can have different kinds of anomalies. But even in the absence of data redundancy, you can have data anomalies. So for example, we saw for insertion and deletion, you don't essentially need redundancy to be present for an anomaly to happen, right? You can insert data which might lead to the creation of dummy data or require the creation of dummy data, has no meaning, right? You might delete a certain record or delete a certain data, and that might also lead to a removal of record that is not intended, right? So these are some of the examples or some of the shortcomings that was present in the file system. And essentially, the reason behind that, there is actually a root cause behind all of this. And the root cause is file systems where structural and data dependent. So this was a major cause. When we move towards the database systems, we are trying to basically address this kind of particular issues that we have, right? So what that means is that anytime there was a change with respect to what information or what data you're trying to store, then you would have had to change all the programs, all the procedures that is responsible for managing your file systems, because all of them are structurally dependent. That is dependent on the structure of the computers or the files that you have designed. And that example we discussed when we were trying to add more courses to this particular file. That is, anytime we would want to add a course, we will have to change essentially the whole structure of our files, right? And all the programs that were responsible for managing that structure needs to be rewritten, which will add on to the development time. And data dependency means that if you have to change, let's say, instead of storing the date of birth in this particular format, you want to change that to year, month, and then date. And instead of 4 digits, you want to make it 2 digits. So now that the format of your data is changed, the nature of your data has changed, now you would have to rewrite all the programs that is responsible for managing the entire file and not just that particular column, right? So file systems were essentially structurally and data dependent. And that led to all of these different anomalies, that is insertion anomalies and deletion anomalies in the absence of data redundancy, right? So you can have insertion and deletion anomalies in the presence of data redundancy, but you can also have them in their absence as well, right? So in order to address all of these problems, we came up with the database systems, okay? So what the database systems did is basically they integrated So database systems that is composed of the database server and the database management system basically integrated our view of the data. That is, it separated the layer of the users, that could be the designers, that could be the system administrators, that could be customers, from the view of the data itself. Okay, so it provided a layer of abstraction from the way the data is being stored. And the interactions that we had with the data was only restricted to what are we trying to store, how we will store it, and then what kind of queries we want to execute against it in order to gather some of the information. The underlying structure of how it needs to be managed, or how the operations that we want to do needs to be performed, was not required. We did not need to give it directives in order to do that. In file systems, we would have to exactly tell the file system what needs to be done and how it needs to do it. But here, within the database system environment, that requirement was removed. That is, we did not need to specify how something needs to be done. All we needed to specify is what was required. And then the server was able to process that with the help of the database management systems, right? So whereas the view of the data that we saw here for file systems, where different departments had their own file systems and they were operating on them, what database systems did is you had the HR department, you had the finance department, and then you had customer relation, and then you had, let's say, the R&D department. So now instead of maintaining their own file system, all of them had this DBMS, which is the database management system, which is a set of or a collection of softwares or programs that is pre-written and responsible for managing and executing queries against the database. And then you had your database server, which was essentially responsible for storing the data. Okay, so all of these different departments now had to go through the DBMS and then interact with the database. So this kind of improved the nature of data sharing, which was lacking in the file system domain, right? Because now all of them can share the data, and if any changes were made by one department, it will happen in only a single location, which is storing the data. And then if the other department tries to access that same location, then they will get the up-to-date information. So you see, the nature of the architecture addressed some of the problems. But there is still the problem of design issue, because this design issue that we talked about here does not get resolved just because you're using a database, right? So that is why we are learning about this course. But yes, given the nature of the architecture of database systems, some of the issues were solved, which is inherently about increasing the security of the data, because now there is a layer of abstraction that is provided from people who are trying to access the data versus where the data is being stored, right? It also improves data sharing. It increases the aspect of data consistency, right? And as a result of that, the decision-making process also improves. Okay. So towards the end of this particular lecture slide, when you look at the slides that has been uploaded, you will find some definition, or you will find some pictorial views of the components of the DBMS environment. Okay, so please read that. That's your reading assignment, and then after that you will have the functions of the DBMS. So as far as your reading assignments are concerned, so please, towards the end of chapter 1, read about the components of database system, just a brief overview and its graphical representation. And then there is a set of outlines which talks about the functions of the database management system, right? So these are just text. They are pretty straightforward. There is nothing actually to explain there. So just take a read and get an understanding of what they are talking about. Okay. So other than that, to recap our discussions for today, we discussed some of the basic terms or defined some of the basic terms in this domain. And then we discussed about the importance of a good DB designs. Okay, and then you have a self-exercise. After which we talked about the evolution of data storage, and we talked about the file system and specifically the problems of data redundancy and data anomalies. So specifically, we discussed these problems when we were talking about the importance of a good database design as well. And then finally, we talked about, or we discussed briefly about the architecture of a DB system and how it compares to the file system architecture, and it helps to resolve some of the problem. And after that, you have two small reading assignments. Okay. So in the next class, we will talk about the different data models that are available to us for designing different databases. And we will also take a look into what is known as business rules. Okay, so when we are performing functional and functional requirements analysis, right, and collecting the client requirements to develop our database, what are the basic building blocks of a data model that we need to use, and how to write business rules. And then we are going to take a brief look at different available data models that are there. And then we are finally going to discuss about the different degrees of data abstraction when it comes to database design. Okay, so that will be the content of the next lecture video. All right, so until then, stay safe and take care. I will see you all again in the next lecture video.